Hi guys, welcome to our lecture today on polarity and its relationship to our friend water and solutions, specifically aqueous solutions. So polarity is a concept that I always had a difficult time with, and it haunted me, well into my, my senior year in college. I just didn't have a grasp on it. Simply means Polarity simply means a charge distribution. Doesn't mean you have if you have a charge anywhere, you're going to have a charge distribution. Okay, so any charged molecules are polar. There are some molecules that have a positive and negative region that are explicit, like the water molecule. But look, whenever you see something with a charge on it, it's going to be a polar compound or polar substance. Okay, and that underlies our understanding of why water is behaves the way it does, and why we think it really is going to be the grail for finding life on other planets. Just recently, it's 2 weeks ago, there was news that phosphine, the compound phosphine, was found in the atmosphere of Venus. And of course, it's occurring with, water and water vapor. Venus is like an example of a greenhouse effect gone awry. Ask me about it, I'll tell you all about Venus. Anyway, our next topic is water and solutions. And so you can see this guy up here in the water jug, and he's saying, why is water weird? Why is water weird? Why is water weird? Why is water weird? And the reason it's weird is because it is a molecular compound with ionic character. Okay? So remember, we talked about covalent bonds giving rise to molecules. It's a compound, right? So I have these condition in which electrons are shared between oxygen and two hydrogens, but due to the extraordinary electronegativity of oxygen, it gives rise to ionic character, to partial charges. And you can see here, my GIF stopped working. Maybe we'll see it again. See if I can get it to go. There it goes. You can see some water molecules here, and they're exchanging hydrogens. In fact, these are individual waters, and they're picking up a hydrogen. They're going from H2O to H3O plus. And that's a quality of water. And, of course, water breaks apart into OH and hydrogen ions readily at a steady rate. And we'll look at that as the basis for the pH system as well. Anyway, here's our water molecule. Remember that oxygen has 2 unpaired electrons in its outermost shell. So it forms a bond with water. The hydrogens are held at 109 degrees off center of the oxygens. And you'll see this goofy symbol here, and that is the Greek letter phi, the lowercase phi, and what it signifies is partial negative, partial positive. So that what's that telling you is that I don't have a full charge. Remember, we talked about ionic compounds and how sodium would lose an electron and therefore it would carry on. It would have a full positive charge, +1. Chlorine, on the other hand, would have gained an electron and would have a full charge of -1. Well, in the case of water, in the case of this molecule, I don't have a full charge, but I do have partial charges. And that has to do with this oxygen's location on the periodic table. Remember, it's right next to, it's CNOF, so it's right next to fluorine up at the top of the periodic table. It's extremely electronegative. It loves electrons, and it holds those electrons very close to its nucleus, and it even has the capacity to strip electrons from compounds. In fact, it's holding the hydrogen's electrons closer to its nucleus than hydrogen is. And it creates something called a dipole moment. And a dipole moment is a measure of physical measure of force, and we can measure that dipole moment and its associated forces, and it gives rise to intramolecular or intermolecular interactions called hydrogen bonds. All right, so here's a graphic that shows individual water molecules. They kind of look like Mickey Mouse upside down. So remember, hydrogens are partially positive, oxygen's partially negative. Of course, individual water molecules never exist alone. They're always with their buddies. And these positive charges on hydrogens form attractions, weak electrostatic attractions called hydrogen bonds. Now, we're going to see hydrogen bonds over and over again. And hydrogen bonds are weak bonds, and they're between hydrogen, positively charged hydrogens, and maybe a negatively charged oxygen or other stuff. So I can have hydrogen bonding between amino acid groups or in a protein, or between DNA and nucleic acids, or the nucleotides and nucleic acids. Anyway, we see hydrogen bonds all over the place, but this is our first experience with them. So if I have a hydrogen attached to another molecule, one molecule here, another molecule here, but a bonding between, intermolecular bonding, these are hydrogen bonds, and they're very weak, except when you consider that there's trillions of water molecules. And that creates some of water's weird properties. Okay? Now, since I have this dipole moment, I have a polar molecule, a molecule that has charge distribution. But I don't want you to be misled. If I have a charge, I'm polar, okay? Water, particularly in this case we're looking at in gory detail, has positive charges here and here and negative partial charges here. All right? Of course, polarity can't operate on its own. In fact, the thing about charge is you can't be negatively charged. Polarity and charge is always a relative term. So I can't be negative if there's not some positive nearby. Similarly, I can't be polar without understanding what nonpolar is. And what is a superpolar molecule? I got charge distribution. So what's the opposite of a polar? Well, a nonpolar compound. And our buddies, the hydrocarbons, are particular examples of nonpolar compounds. And the easy way to remember this is the old axiom that oil and water don't mix. That's right. Oil is a hydrocarbon, water is a polar molecular compound, and they don't mix. Oil, nonpolar, hydrocarbon. Anyway, so these interactions between water molecules make water sticky. These interactions between water molecules make liquid water more dense than solid water. Up at the top here, you can see a GIF that shows water undergoing freezing, and you can see that when it's liquid, the water molecules are close together, but as it freezes, it forms a crystalline lattice, and those atoms actually have to move apart. In this illustration here, the GIF at the bottom, I can see some charged molecule in the center that's being surrounded by water molecules. And we say that water is actually the universal solvent. All right, so it breaks down all kinds of compounds, ionic compounds, polar compounds, and that's one of the reasons we think that in order for you to have life-sustaining metabolism, you're going to have liquid water or water associated with high temperatures and pressures. So this polar quality gives rise to a bunch of strange properties, right? Normally when you think about a pure substance like, let's just say I had liquid aluminum, right? If I had a solid aluminum cube and I put it in a liquid aluminum, what would happen? Well, it would drop because typically solids are more dense than liquids. Not the case in the case of water. So I've got ice is less dense than water. I know that because when I drop an ice cube into water, what does it do? Well, it floats. That has important impact on a lot of things, like particularly here just on planet Earth. If you're a fish and you live in a freshwater lake, you can make it through the winter because the ice will form on the surface of the lake and actually act as an insulating barrier so that the lake doesn't freeze all the way through. So that's one important aspect with respect to life about water's or ice's low density. It really points to another sort of a larger thermodynamic consideration, and that is water has a tremendous ability to absorb heat. Okay, it has what's called a very high latent heat or phase heat, and so in order for me to change water from a liquid into a gas, I've got to put lots and lots of energy relative to other substances, all right? And you know this. If you dropped like isopropyl alcohol onto a table, it would evaporate pretty rapidly. That's because isopropyl alcohol is nonpolar. Now, if I poured water next to it, it would take much longer for that water to evaporate because it has all these polar qualities. It sort of sticks together. It doesn't want to escape into the gaseous phase. Similarly, when gaseous water vapor condenses, it releases tons of energy. And this explains why hurricanes can be so devastating, right? I've vaporized oceanic marine water. It goes into a gaseous phase. It rises. As it gets higher and higher in the atmosphere, it hits colder and colder atmospheric temperatures. It condenses. Well, that energy doesn't go away. That energy is transmitted into the atmosphere, and that's why we have circulating winds associated with hurricanes. So not only that, but like in our bodies, water tends to sort of like moderate things. And this is sort of one of the big problems with what's happening in our oceans is that, we're getting hotter and hotter at the equator. And, normally we're able to like dissipate heat around the globe. And one of the greatest concerns for climatologists is the idea that we might disrupt the oceanic conveyor belt. So if you want to know about that, ask me about that as well, but that's not in our scope of this course. So water's got a high latent heat. Liquid water's more dense than ice. Water's both adhesive and cohesive. So water sticks to itself. It's coherent, right? And it allows for a process called capillarity, right? I can get water to like kind of be sucked up the little tubes of a tree, the xylem, and flown hundreds of feet in the air, 350 feet in the air. That requires tremendous pressure. And it's also adhesive, so it will stick to other stuff as well. And then finally, last but not least, water is this universal solvent, right? And so if I threw an ionic compound, sodium chloride, into water, it would immediately dissolve. So latent heat. In physiological systems, latent heat allows me to maintain a steady body temperature, right? So, I'm like 75% water. And so I can absorb a lot of heat, but I can also hold a lot of heat. And that allows for me to maintain homeostasis. These water molecules are sticking to one another. And so I take advantage of that in the circulation of fluids to the body as well. And then finally, one of the things that's interesting about water is that because of its inherent instability, right? Because water is made up of oxygen that's super electronegative and these hydrogens that are less electronegative, they, in a way, they don't care about their electrons as much. And because oxygen is so electronegative, what it does very often is it will actually steal the electrons from one hydrogen and let it go. And then you form this OH minus called the hydroxyl. It's got an oxygen, a hydrogen, and it's carrying its own pair of or own extra electron for a full negative charge, and it lets let go a lone proton, a lone hydrogen, and of course that lone hydrogen will immediately be attracted to its neighbors, oxygens, to form the hydronium ion, and so that gives us the basis for the pH system. The pH system. The pH system is a measure of hydronium ion concentration in solution. Okay, so solutions, aqueous solutions particularly, have a measure of pH. That is, how many of these guys are present? And the answer is 10 to the negative 7 molar in solution. That's the concentration. And we use P. Little p actually represents the negative log function, and the H refers to hydrogen ion concentration. So pH is the negative log of the hydrogen ion concentration. And in solution, in a bucket of water, there'd be a 10 to the negative 7 molar concentration of the species, which immediately becomes the H3O ion, the hydronium ion, right? But we're measuring H. So aqueous solutions are interesting. And one of the most interesting things about aqueous solutions is the formation of acids and bases. And when we talk about pH, we talk about acids and bases. So remember, acids and bases can be defined a lot of ways. One of the common ways is talk about a Bronsted or Lewis-Bronsted base acid thing. Anyway, acids are hydrogen ion donors. And the perfect acid to remember is hydrochloric acid. All right, so hydrochloric acid undergoes dissociation, just like what it does, into a hydrogen ion. It donates hydrogen ions and the chloride ion. All right, so these guys are floating around in water. On the other hand, bases are hydrogen ion acceptors. The classic base is sodium hydroxide, Li. And when sodium hydroxide dissociates, it dissociates into the sodium anion and the sodium cation and the hydroxyl anion. And this OH group is a hydrogen ion acceptor. As soon as this guy is present, it scavenges up any lone hydrogen ions. It becomes water. Well, acids and bases are nothing to screw around with. And you don't want to have hydrogen ions donated to your skin. You don't want to have hydrogen ions scavenged from your skin. Either you get a corrosive burn. Okay? Now, I'll probably put together an exercise for you, an activity discussing pH. But listen, counterintuitively, here's the thing that was always a problem. I knew that acids were hydrogen ion donors, right? So they must have lots of hydrogen ions, right? And pH was a measure of hydrogen ions. So acids should have a high pH, right? Wrong. Acids have a low pH. Sodium hydroxide, a base, is a hydrogen ion acceptor, so there shouldn't be very many hydrogen ions, right? So the hydrogen ion concentration should be low, so the pH should be a low number. Wrong again. And I'll have a fun activity for us to discuss the mathematics of the negative log function. But, acids and bases can be fun to fool around with. And, of course, you've got lots of very specific pH balance mechanisms, and we'll talk about that in some gory detail soon. Don't screw around with acids or bases. Both of them will mess you up.